The dot plot shows the number of hours of daily driving time for 14 school bus drivers. Each dot represents a driver. So for example, one driver drives 1 hour a day. Two drivers drive 2 hours a day. One driver drives 3 hours a day. It looks like there's 5 drivers that drive 7 hours a day. Which of the following is the closest estimate to the percentile rank for the driver with a daily driving time of 6 hours? And then they give us some choices. Which of the following is the closest estimate to the percentile rank for the driver with a daily driving time of 6 hours? So pause the video and see if you can figure out which of these percentiles is the closest estimate to the percentile rank of a driver with a daily driving time of 6 hours. Looking at this data right over here. All right, now let's work through this together. So when you think about percentile, you really want to think about, so let me write this down. When we're talking about percentile, we're really saying the percentage of the data that, and there's actually two ways that you could compute it. One is the percentage of the data that is below the amount in question. The other possibility is the percent of the data that is at or below. That is at or below the amount in question. So if we look at this right over here, let's just figure out how many data points, what percentage of the data points are below 6 hours per day. So let's see, there are, I'm just going to count them, 1, 2, 3, 4, 5, 6, 7. So 7 of the 14 are below 6 hours. So we could just say 7, if we use this first technique, we would have 7 of the 14 are below 6 hours per day. And so that would get us a number of 50%. That 6 hours is at the 50th percentile. If we want to say what percentage is at that number or below, then we would also count this one. So we would say 8 or 8 out of 14. 8 out of 14, which is the same thing as 4 out of 7. And if we want to write that as a decimal, let's see, 7 goes into 4.000. We just need to estimate. So 7 goes into 45 times, 35. We subtract. We get a 5, bring down a 0, goes 5 times. So it's just going to be 0.5 repeating. So 55.5555%. So either of these would actually be a legitimate response to the percentile rank for the driver with a daily driving time of 6 hours. It depends on whether you include the 6 hours or not. So you could say either the 50th percentile or roughly the 55th, well, actually the 56th percentile if you wanted to round to the nearest percentile. Now if you look at these choices here, lucky for us, there's only one choice that's reasonably close to either one of those, and that's the 55th percentile. And it looks like the people who wrote this question went with the calculation of percentile where they include the data point in question. So everything at 6 hours or less, what percentage of the total data is that?
Here's the second problem from ck12.org's AP Statistics Flexbook. It's an open source a textbook essentially. I'm using it essentially to get some practice on some statistics problems. So here, number 2, the grades on a statistics midterm for a high school are normally distributed with a mean of 81 and a standard deviation of 6.3. All right. Calculate the z-scores for each of the following exam grades. Draw and label a sketch for each example. We could probably do it all on the same example, but the first thing we'd have to do is just remember, what is a z-score? What is a z-score? A z-score is literally just measuring how many standard deviations away. How many standard deviations away from the mean? From the mean. From the mean, just like that. So we literally just have to calculate how many standard deviations each of these guys are from the mean, and that's their z-scores. So let me do part A. So we have 65. So first we can just figure out how far is 65 from the mean. Let me just draw one chart here that we could use the entire time. So if this is our distribution, let's see, we have a mean of 81. So we have a mean of 81. That's our mean. And then a standard deviation of 6.3. So our distribution, they're telling us that it's normally distributed. So I can draw a nice bell curve here. They're saying that it's normally distributed, so that's as good of a bell curve as I'm capable of drawing. This is the mean right there at 81. And the standard deviation is 6.3. So one standard deviation above and below is going to be 6.3 away from that mean. So if we go 6.3 in the positive direction, that value right there is going to be 87.3. If we go 6.3 in the negative direction, where does that get us? That goes to what? 74.7? 74.7. Right, if we add 6, it'll get us to 80.7, and then 0.3 will get us to 81. So that's one standard deviation below and above the mean, and then you would add another 6.3 to go to 2 standard deviations, so on and so forth. So that's at least a drawing of the distribution itself. So let's figure out the z-scores for each of these scores. So 65, or each of these grades. 65 is how far? 65 is, it's maybe going to be here someplace. So we first want to say, well, how far is it just from our mean? From our mean. So the distance is, we just want a positive number here. Well, actually, you want a negative number because you want your z-score to be positive or negative. Negative would mean to the left of the mean, and positive would mean to the right of the mean. So we say 65 minus 81. So that's literally how far away we are. But we want that in terms of standard deviations. So we divide that by the length or the magnitude of our standard deviation. So 65 minus 81. Let's see, 81 minus 65 is what? It is 5 plus 11. It's 16. So this is going to be minus 16 over 6.3. And take our calculator out. And let's see, if we have minus 16 divided by 6.3, you get minus 2.54. So approximately equal to minus 2.54. That's the z-score for a grade of 65. Pretty straightforward. Let's do a couple of more. Let's do all of them. 83. So how far it is away from the mean? Well, it's 83 minus 81. It's 2 grades above the mean. But we want in terms of standard deviations. How many standard deviations? So this was part A. A was right here. This was we were 2.5 standard deviations below the mean. So this was part A. 1, 2, and then 0.5. So this was A right there, 65. And then part B, 83. 83 is going to be right here, a little bit higher. We're right here. And the z-score here, 83 minus 81, divided by 6.3, will get us, let's see, clear the calculator. So we have, well, 83 minus 81 is 2, divided by 6.3, it's 0.32, roughly. So here we get 0.32. So 83 is 0.32 standard deviations above the mean. And so it would be roughly 1/3 of the standard deviation along the way, right? Because this was one whole standard deviation. So we're 0.3 of a standard deviation above the mean. Choice number C. Or not choice, part C, I guess I should call it. 93. Well, we do the same exercise. 93 is how much above the mean? Well, it's 93 minus 81 is 12. But we want it in terms of standard deviation. So 12 is how many standard deviations above the mean? Well, it's going to be almost 2. Let's take the calculator out. So if we get 12 divided by 6.3, it's 1.9 standard deviations. Its z-score is 1.9, which means it's 1.9 standard deviations above the mean. So the mean's 81. We go one whole standard deviation, and then 0.9 standard deviations, and that's where a score of 93 would lie right there. Its z-score is 1.9. All that means is 1.9 standard deviations above the mean. Let's do the last one. I'll do it in magenta. D. Part D. A score of 100. A score of 100. We don't even need the problem anymore. A score of 100. Well, same thing. We figure out how far is 100 above the mean. Remember, the mean was 81. And we divide that by the length or the size or the magnitude of our standard deviation. So 100 minus 81 is equal to 19 over 6.3. So it's going to be a little over 3 standard deviations. And in the next problem, we'll see what does that imply in terms of the probability of that actually occurring. But if we just want to figure out the z-score, 19 divided by 6.3 is equal to 3.01. So it's very close, 3.02 really, if I were to round. So it's very close to 3.02. Its z-score is 3.02, or a grade of 100 is 3.02 standard deviations above the mean. So remember, this was the mean right here at 81. We go 1 standard deviation above the mean, 2 standard deviations above the mean. The 3rd standard deviation above the mean is right there. So we're sitting right there on our chart, a little bit above that. 3.02 standard deviations above the mean, that's where a score of 100 would be. And you can see the probability, the height of this, that's what the chart tells us. It's actually a very low probability. And actually, it's not just a very low probability of getting something higher than that, because we learned before in a probability density function, the probability, if this is a continuous, not a discrete, the probability of getting exactly that is 0 if this wasn't discrete. But since this is a scores on a test, we know that it's actually a discrete probability function. But the probability is low of getting higher than that, because you can see where we sit in the bell curve. Well, anyway, hopefully this at least clarified how to solve for z-scores, which is pretty straightforward mathematically. And in the next video, we'll interpret z-scores and probabilities a little bit more.
Before applying to law school in the U.S., students need to take an exam called the LSAT. Before applying to medical school, students need to take an exam called the MCAT. Here are some summary statistics for each exam. So the LSAT, the mean score is 151 with a standard deviation of 10. And the MCAT, the mean score is 25.1 with a standard deviation of 6.4. Juwan took both exams. He scored 172 on the LSAT and 37 on the MCAT. Which exam did he do relatively better on? So pause this video and see if you can figure it out. So the way I would think about it is, you can't just look at the absolute score because they are on different scales and they have different distributions. But we can use this information if we assume it's a normal distribution or relatively close to a normal distribution with a mean centered at this mean. We can think about, well, how many standard deviations from the mean did he score in each of these situations? In both cases, he scored above the mean, but how many standard deviations above the mean? So let's see if we can figure that out. So on the LSAT, let's see, let me write this down. On the LSAT, he scored 172. So how many standard deviations is that going to be? Well, let's take 172, his score, minus the mean. So this is the absolute number that he scored above the mean. And now let's divide that by the standard deviation. So on the LSAT, this is what? This is going to be 21 divided by 10. So this is 2.1 standard deviations. Deviations above the mean. Above the mean. You could view this as a z-score. It's a z-score of 2.1. We are 2.1 above the mean in this situation. Now let's think about how he did on the MCAT. On the MCAT, he scored a 37. The mean is a 25.1. And there is a standard deviation of 6.4. So let's see, 37.1 minus 25 would be 12, but now it's going to be 11.9. 11.9 divided by 6.4. So without even looking at this, so this is going to be approximately, well, this is going to be a little bit less than 2. This is going to be less than 2. So based on this information, and we could figure out the exact number here. In fact, let me get my calculator out. So you get the calculator. So if we do 11.9 divided by 6.4, that's going to get us to I'll just say approximately 1.86. So approximately 1.86. So relatively speaking, he did slightly better on the LSAT. He did more standard deviations, although this is close. I would say they're comparable. He did roughly 2 standard deviations if we were round to the nearest standard deviation. But if you wanted to get precise, he did a little bit better, relatively speaking, on the LSAT. He did 2.1 standard deviations here, while over here he did 1.86 or 1.9 standard deviations. But in everyday language, you would probably say, well, this is comparable. If this was 3 standard deviations and this is 1 standard deviation, then you'd be like, oh, he definitely did better on the LSAT.